Hello, welcome to my YouTube channel. We are now on lesson 4 in nuclear and particle physics, and we are going to be talking about binding energy and mass defect today. And in our lesson outline, we are going to first of all demonstrate the concept of mass defect and binding energy, explain the meaning of mass defect and the meaning of binding energy, as well as discussing Einstein mass energy relationship. Demonstrating binding energy and mass defect. Now, the nucleus of every atom contains protons which are positively charged and neutrons which are neutral particles. The fundamental law of electrostatics tells us that like charges repel, which means the protons in the nucleus repel each other. And if there was no other force in the nucleus to oppose this repulsive force between the protons, then there will be no nuclei. This means there will be no atom, there will be no material, and there will be no life. But it is now known that there is another force called a strong force which overcomes the repulsive force between the protons and keep the nucleus intact. This force is attractive in nature and acts between protons, neutrons, and between protons and neutrons. Hence, to completely separate the nucleons apart, energy is required, which is equivalent to the energy that binds the nucleons together. Now let's consider, for example, a helium nucleus, which has two protons and two neutrons. So suppose we supply energy to it sufficient enough to separate the nucleons apart as shown. I have used the symbol Mn to mean the mass of the nucleus and Mcn to mean the sum of the masses of the constituent protons and neutrons. Now I have with me data for the mass of the nucleus of a helium atom, mass of proton and mass of neutron from Wolfram alpha. We can get the sum of the masses of the constituent nucleons that makes up the nucleus of a helium atom by adding the masses of the two protons to the masses of the two neutrons to have that value. And if we compare the MCN value to the MN value, we realize that MCN is greater than MN. That is, the sum of the masses of the constituent nucleons that makes up the nucleus of a helium atom is greater than the mass of the nucleus of the atom itself. It looks simple, but the question arises. How can the sum of the masses of the particles that makes up a nucleus be greater than the mass of the nucleus itself? What we would normally expect is that the sum of the masses of the particles that makes up the nucleus should be equal to the mass of the nucleus. But in this case, it's greater. There is a reason for this, which we are going to see very soon. Now, this is not only true for helium, it is true for all nuclei. Now, are going to define what mass defect is. Mass defect is simply the difference between the sum of the masses of the constituent nucleons of a particular nucleus and the mass of the nucleus itself. That means if we take MCN minus MN, we obtain what we call the mass defect. You can also call it the missing mass. Again, mass defect theta M, which is a symbol, is equals to MCN minus MN. MCN is the sum of the masses of the constituent nucleons that makes up the nucleus, and MN is the mass of the nucleus. Now, in most standard textbooks, Mn is actually denoted by the symbol M in bracket A, comma Z, and the reason for this is because AZ are the two main things that characterize a nuclide. We have talked about nuclide symbol, and MCN is equal to the total number of protons, which is the atomic number, times the mass of one proton plus the total number of neutrons times the mass of one neutron. And the total number of neutrons, of course, is equal to the mass number minus the atomic number. Now, we have that expression. If we substitute Mn and Mcn into the formula for mass defect, we have that expression. And if we can calculate mass defect for the helium nucleus that we have considered, we'll substitute the values that we obtain. We have 0.03 U as the mass defect. Now, most times, students are not given the mass of the nucleus, they are given the mass of the atom. And when you are given the mass of an atom, you know that an atom contains protons, neutrons, and electrons. So, which means the mass of the atom that has been given to you has the mass of the electrons. So, you have to add the mass of the total number of electrons to the mass of the constituent particles before subtracting the mass of the atom. And of course, the number of electrons in a neutral atom is the same like the atomic number Z. So that is why you have Z times Me, mass of electron. All right, binding energy, the meaning. Now let's come back to the equation where we had the nucleus with nucleons held together by strong forces. And we said that if we wish to separate the nucleons of this nucleus apart so that they are completely separated, we need to supply an amount of energy which is equivalent to the energy binding the nucleons. And that's what we call binding energy. Binding energy is the energy needed to completely separate the nucleons of a nucleus apart. Now, why was there a mass defect? We talked about it, mass defect. Now, we are going to write that equation in the reverse order. If energy is needed to break a nucleus into its constituent nucleons, then if the constituent nucleons come together, they can form the nucleus again. And if energy was needed to break it, then when the nucleus is formed, energy will be released. Now, if you look at that equation, we have said that the mass of the constituent nucleus is greater than the mass of the nucleus. And it is clear that the only reasonable explanation to give is that part of the mass of the constituent nucleons has been transformed to the energy that has been produced. So, the missing mass is as a result of transformation of part of the mass of the constituent nucleus into energy. Now, since mass can be transformed into energy, Einstein therefore proposed that the amount of mass transformed should be proportional to the energy that will be produced. That means a larger mass transformation leads to a greater amount of energy released. And that can be expressed mathematically as shown. And if we want to check what K represents, we found out that is you can make K the subject of the formula, substitute the unit of energy and mass, and you realize that you come out with meter squared per second squared, which is the unit of the square of a speed. Now, energy release is usually in the form of heat or infrared radiation or any other form of electromagnetic radiation. So, which means that K there represents the square of the speed of light. And we now have that relationship E equals to delta mc squared. This is what is usually called Einstein mass energy relationship, and it tells us that mass can be transformed to energy and energy can be transformed to mass. Binding energy is actually the energy equivalence of the mass defect. We've come to the end of lesson 4. Our next lesson will be on solving problems. I'll be uploading series of solutions, and at the end of it all, I will give some exercises. Now, if this is your first time of visiting my channel, I would like that you like, share, subscribe, and click on the notification bell to be notified when the next video drop. Thank you very much. This is Physics with Omia.